Welcome back, guys. Thank you so much for watching our classes on this channel. You guys have been so wonderful. If you're just new here, please subscribe so that you get notifications about our new classes. And to those who are been with us for a while, I welcome you back again. I'm still Mercy Bome by name, your educational consultant in chemistry and in mathematics. Like you know that I work more in chemistry and mathematics. I'm also here to give us a topic on chemistry called radioactivity. Radioactivity is also taught in the tertiary institution, most especially as chemistry 214, especially as chemistry 224, whichever course code your institution gives to it, it is still nuclear chemistry. Another nuclear chemistry, we have radioactivity. Radioactivity, just as it is being displayed on your screen, radioactivity was discovered by someone called Henry Becquerel in 1896. But it was the Curies, that is Mary and Paul Curies, that proved the existence of radioactive element. Now the fact that Henry Becquerel was the one who discovered it, some people had already known its existence right from time, which has been proved by the Curies. So it was Henry Becquerel who discovered the usefulness, let me put it like that, in 1896. And when we talk about radiation or radioactivity, it is, the disintegration of an element, just like that, by changing, and at the end of the day, the mass changes, the atomic mass changes too, without prompting. So we have the real definition of radioactivity. Radioactivity is a radiation of energy without prompting. Radioactivity is also defined as a spontaneous disintegration of decay of nucleus of a radioactive element or atom, and the emission of particles or radiation. Some of the examples of radioactive elements, we have uranium-235, we have thorium, we have platinum-234 and 227 respectively. That also leads me to talk about natural radioactive element. These natural radioactive elements are said to bring forth radiations without prompting them, without any light consequence, without any determinant. They just flow out radiation without prompting. Now, under these radiations, we have three major kinds of radiations. We have the alpha radiations, we have the beta radiations, and we have the gamma radiations. Talking about the alpha radiation, let me give you some time to check them on the screen. I'll be right back. Welcome back, guys. Now, in as much as radiation as is a spontaneous disintegration of element, these things happen around us. These things happen in places, in the lab, in the chemical laboratories, and how do we dictate them? Just like that's been displayed on the screen about alpha, beta, and gamma radiations, how do you discover, how do you dictate that this radiation is an alpha, this one is this one is that? We have three methods of detection of radiation. Yes, three ways, three machines that were discovered, and more than three ways, but the major ones I'll be talking about is five. We have the spintariscope, the scintillation counter, the gigamolar counter, the Wilson cloud chamber, the bubble chamber, and amongst all we still have the ionization chamber and many others. But the spintariscope is very good, So as I said, let me give us some time to also check them.
I love you, Lord. Oh, your mercy never fails me. I've been held in your hand from the moment that I wake up until I lay my head. Oh, I will sing of the goodness of God. 'Cause all my
On the screen. Welcome back. So, what happens when an element disintegrates either by the alpha radiation or the beta radiation or the gamma radiation? We have laws of radioactivity. And the laws of radioactivity, one of the first laws states that when an element disintegrates by the alpha radiation, it's the mass number and the atomic number reduces to become one of those on the left hand side of the periodic table. This is what I mean. When we have nitrogen mass number is 14, while the atomic number is 7. And we were told disintegrates by an alpha particle. An alpha particle most times uses He as a disintegrating element. Now, if I'm to, it reduces. So I have, when this disintegrates, I have 10, 5. It becomes the one of carbon. And if we check very well, carbon is on the left-hand side of the periodic table. Also, when an element disintegrates by beta particle, we have 14, 7, and plus this. Most times they use this. Most times they use this. So our answer still becomes 14, 6, which is still nitrogen. But the gamma radiation does not change. It doesn't change anything. It is neutral. You still have your 14, 7, and as the same. So the beta radiation confirms the second law of radioactivity that says that when an element disintegrates by the emission of beta particles, it becomes the element with chemical properties of an element at the right hand side of the periodic table. Now, let me give us some of these questions, that are being used in radiations. Most times you're familiar with them. Yeah, something like this. When you're asked that, what is the half-life? Taken to disintegrate nitrogen to um, hydrogen. Hydrogen one. Now we all know that the first thing we'll do is we'll begin to divide this divided by 7 divided by 2. You have half-life is always written in T. We have 3.5. 3.5 divided by 2. We have 1.75. 1.75 divided by 2. We have 0.88, blah blah blah. Okay? So now, majorly we'll say the T half is always 1/2 times 1/2 times 1/2. And this is 1/8. So we'll say that it takes 1/8 of the time taken for nitrogen to disintegrate into hydrogen. I know we're very much familiar with that. But because we're moving to chemistry 214, there are more technical questions that goes beyond using this formula. And that's what I'll be talking about welcome back. Checking through the um, formulas on board. These are some of the clues I want us to have. I don't want to take much of our time on I would have proven how these formulas came true. But this is a summary of all the formulas we're going to be using. Let's take note of them. And like I said earlier, that it's not about TF, time taking, blah 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 alone. We also have some technical questions that requires you to use some of this. For instance, when we have questions like the one above, so question like a radioactive element has an initial count rate of 1,400 counts per second, measured by a proportional counter, and this falls to 1,800 counts per minute in 15 hours. Calculate the half-life of the radioactive element. Now, we have counts there. Count, 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 count. Now, from this, we have the N till the N naught. The N is always a final count, while the N naught is the initial count. Now, the initial count that was told us there is 1,400 counts per second. Let's say CPS. Yes. So, and the final one given to us, which is our NT, is 1,800. But we're giving in counts per minute, that is CPM. Whereas everything must be the same. So I'm converting this to seconds. So if we have 1,800 per minute, so which means converting it to seconds, I should have 1,800 over 60 will give me 30 counts per second. So I have the same values now. And the time taken was 15 hours. Like I said earlier, I want everything to be the same. So I have converted 15 hours to seconds, so be times 60 times 60. So I should have 54,000 seconds. But we have to find something. We have to find the half-life of the radioactive element. Now, talking through these formulas, the half-life. Using this, because we're given the time, using this, let's check what the half-life will be. So we have lambda. That is, before we can get the half-life, we need to get what lambda is. We have minus 2.303 all over t log 10 of the nt of the n naught. So we have our lambda to be minus 32303 all over 54,000, then log the final count over the initial. So by the time you multiply everything using your log, using everything, your lambda should give you 7.12 times 10 raised to power minus 5 per seconds. Lambda is always per second, that is x raised to power minus 1. Now because we have, sorry I didn't write one of the formulas. So because I've gotten my lambda, it is easy for me to get my TF. Since TF is 0.693 over lambda, therefore my TF, that is the half-life, The half-life taken is 0.693 all over 7.12 times 10 raised to the power minus 5. So by the time we're done calculating everything, our T half should give us 9,733.146 seconds. So I just want to make it in hours because this is too much for a second. So I have divided by 3,600. Therefore, my T half is 2.70 hours. I think this is still very factual. So the half-life taken for these to disintegrate into this is 2.70 hours. So let's move to number 2. So the question one asks B. It says if the initial number of atoms in another sample of this element is 4.5 times 10 raised to the power 19, how many atoms has decayed in 28 hours? That is, if we still use the same lambda, which is 7.12 times 10 raised to the power minus 5 seconds. So therefore we have our n naught, the one we're given to be 4.5 times 10 raised to the power 19 atoms. Therefore, and we're given time in 28 hours. Converting this to seconds, should have 28 times 3,600. 28 times 3,000. So by multiplying this, we have 1,008,00. That's 100,800 seconds. And we're looking for final count. And because we still have this formula here, you can decide to say lambda is equal to minus 2303 all over T log nt over n naught. So this is 7.12 times 10 raised to the power minus 5 over seconds is equal to this all over 100,800 log. We've now been given a final term all over 4.5 times 10 raised to the power 19. Now, we therefore have, by the time we'll cross multiply everything, looking for nt, our nt should give us minus 9.1167 times 10 raised to the power 19 atoms. And because the question says how many atoms has been decayed, it means we're adding both. If the n naught used in the first one gave us the answer, and the one changed, they also give us another answer. How many atoms has decayed together? Therefore, we have the number of atoms that has decayed would therefore be 4.5 times 10 raised to the power 19 minus 9.1167 times 10 raised to the power 19. By the time you add, you should have 13.6167 times 10 raised to the power 19. So this is the number of atoms that has also decayed. The number of atoms that has decayed. The second question says, find the from the question, our T is unknown. We're given our N naught to be 1,200 CPS, then our NT to be 600 CPS2, then we're given the half-life to be 96 seconds. Therefore, let's not forget that our formula still remains lambda is minus 23 over t. This is the formula we ought to use. This is the formula that carries everything we need to find here. Now, we don't know what our lambda is, but we have a formula here that says Tf is equal to 0.693 over lambda. So if I'm to make lambda the subject of the formula, I have lambda is equal to 0.693 over lambda. Therefore, my lambda will become 0.693 all over plus my Tf 96. Therefore, if I divide using your scientific calculator, you should have 0.0072 per seconds. Let's not forget. So with this, I can use this formula now. So I have therefore I have 0.0072 is equal to minus 2.303 over t log 10 of 600 over 1,200. I hope you're following. Now we have 0.0072 is equal to minus 3.303 over t. Break this down. I should have log 10, 1 over 2. Yes. Therefore, I have over t log 10 of 0.5. By the time you press your calculator, the log 10 of 0.5 should give you minus 0.3010. So I have 0.0072 to give me, multiplying both together, I should have a positive number all over t, making t the subject of the formula. Therefore, I should have t is equal to 0.0693 all over 0.0072. My t, use your calculator, will give you 9.629 seconds. So this is the end of nuclear chemistry radioactivity. I hope to get more questions on this particular nuclear chemistry type. But if you have some and you feel I should help you in calculating them, in solving them, please just drop them in the comment section. I will definitely reply you. Please do not to subscribe, share this video, and like. Love you guys.